Let's start with the concept of stress. We know that when we apply an external load on a deformable body, there is some deformation in the body. And it doesn't matter how small it is, but still there is some amount of deformation. Let's take a bar which is subjected to a load P as shown in the figure A. Due to this load, there is a deformation in the bar. Assume that the bar is extended up to section AA and the deformation is delta. From the equilibrium point of view, this action should be opposed or reacted by some internal force. The value of total internal force will be R1 plus R2 plus R3 and so on. Now, it is not possible to measure the internal force. To measure the internal force or reaction, we must balance it with the external force applied. It means we must apply the force balancing equations. Three conditions can be applied between total internal reactions delta R and external load P. First, when the total internal resistance force is greater than the applied load P. But if it happens that the material reaches at section II above the section AA, and that is not possible. Second condition is when the total internal resistance force is less than the applied load P, then the material reaches up to section 22, just below the section AA as shown in the figure. But it is not a feasible condition. The third condition, when the total internal resistance should be equal to the applied load P, then the material reaches up to section AA, and this is also the condition of static equilibrium. So, from the above third condition, we can say that delta R is equal to R1 plus R2 plus R3 up to Rn, and this is equal to P. We know that the stress is the total internal resistance offered by the body. Let area of cross section of the body be A and the total resistance be sigma R. For static equilibrium, delta R is equal to P. Let's write it down. Let area of the cross section of the body be A and the total resistance be delta R. So for static equilibrium, as we know that delta R is equal to P, that is where P is externally applied load. We can see it from the above figure. Hence, resistance, that is stress at a point, will be delta R upon A. This can also be written as P upon A. Hence, resistance or stress at a point will be sigma R upon A, and it can also be written as P upon A. So, from the whole analysis we did so far, stress can be defined as total resistance per unit area at a point, and the symbol sigma is used to represent stress. Hence, we can say that sigma is equal to P upon A, where P is the applied load and A is the area of the cross section. The analysis of stress which we have done now, there is an assumption that stress is uniformly distributed over its cross section. Hence, stress is the same for the whole section and for a point, that is average stress, and the instantaneous stress are the same. If the stress distribution is not uniform over the cross-sectional area, then we define the stress by considering small area delta A, which is subjected to small load delta F. If the total load is F, then we can say that sigma is equal to delta F upon delta A. The above expression is for average stress. To define the instantaneous stress at a point, we must apply a limiting load, that is delta, which approaches towards zero. Hence, mathematically, instantaneous stress is defined as sigma is equal to limit A tends to 0, where A is the cross-sectional area which tends towards 0, and delta F upon delta A. Hence, we can say that sigma is equal to limit A tends to 0 or delta A limit tends to 0. Hence, we can say that sigma is equal to limit delta A tends to 0, sigma F upon sigma A. Now, let us look at units of stress. The basic unit of stress in SI units or the international system is Newton per meter square or Pascal. We know that 1 megapascal is equal to 10 to the power 6 Pascal. 1 gigapascal is equal to 10 to the power 9 Pascal. Also, 1 kilopascal is equal to 10 to the power 3 Pascal. Sometimes 1 Newton per meter square units are also used because this is an equivalent system to megapascal. Till now in this lecture we have learnt about the concept of stress, its definition, average stress and actual instantaneous stress. And from the above analysis we conclude that stress is due to resistance. If the resistance is 0, then the stress automatically is 0. Secondly, from the definition of stress, we can see that it only depends on the load and cross-sectional area. Third, the stress is not measurable quantity. It can only be calculated after measuring the strain by experimental techniques. Fourth, because stress is total resistance, it is not the property in the next. Because stress is total resistance, it is not a property. In the next lecture, we will discuss the tensor quantities and the difference between stress and pressure. Thank you for watching this video. Please do subscribe our channel Ekeeda.